Okay, hello everyone. My name is Sonan Maiman. I am a student of macroeconomics and also econometrics. I am a lecturer at IBA. I did my undergrad from LUMS, Lahore in Pakistan, and I did my MPhil in economics from University of Oxford, which I completed last year. So this is lecture 3 in the series of lectures, which are 4 lectures in total, and we'll have lecture 4 tomorrow, which is on computational linguistics. Okay, um, and especially latent ratio allocation. Uh, Lectures 1 and 2, which were conducted in December 2020, were about regularization-based estimators such as lasso and ridge regression and dimension reduction and that kind of thing in lecture 1, and along with an introduction to machine learning in general, and especially the variance bias trade-off, which is a characteristic of most machine learning problems. In lecture 2, we covered a very interesting topic, which was the multi-armed bandit problems. And these are sort of modern adaptive treatment assignment technologies. And this was a very interesting topic. And we covered these two things in the first 2 lectures. And the lecture slides for the first 2 lectures, as well as are available on my GitHub link, which I've shared in the chat. Okay. And all the 4 lecture slides will be available over there. The YouTube video recordings for the first 2 lectures are available on IBA's YouTube page. Okay. And towards the end of the lecture, we can probably share that too. And we've already shared it in the email that we sent to the people who are based at IBA. Okay. So this lecture is lecture 3, and this is about deep learning or deep neural networks. Okay. And specifically, we'll be covering deep feed-forward neural networks because we don't have time for covering convolutional networks and recurrent networks. And a convolutional network is also a special kind of deep feed-forward network, but we'll definitely not cover recurrent networks in which you can have backward connections. Okay. Um, so the main sort of ideas, the sort of overview of this lecture is that first we'll start with sort of a theoretical description of what a deep feed-forward network is, and followed by the choice of various choices that one has to make in the optimization routine that one is implementing for this neural network, including the choice of the loss function, also called the cost function, and what kind of gradient-based optimization algorithm to use, choice of hidden units, choice of output units, how to define the network architecture, which means a number of layers, a number of units, hidden units, and the pattern of interconnections between them. I'll come to these things. And backpropagation is a particular efficient algorithm for calculating derivatives, which could be applied generally as well, not just in neural networks, but it's especially used very widely in neural networks, along with stochastic gradient descent, which is an algorithm that is used for gradient-based learning of the parameters in the model. Okay. We'll also have a brief discussion of regularization. Lecture 1 was actually all about regularization. So I just have like literally 1 slide on it. And because it's really the same idea, you just augment the loss function with some measure, some sort of penalty term if you have a penalty term based regularization. But early stopping is an algorithm which is particularly used for regularization in the neural networks context. And we will discuss that briefly. That was not covered in lecture 1. And lastly, we'll have a couple of applications on the recent economic literature. If you have time, we'll cover both of them, but we'll definitely cover the first one, which is application in the context of solution of nonlinear DHCE models in macro. And if you have time, we'll cover the second one as well. In any case, I'll have the lecture slides available on my GitHub page. And as I also made clear in the first lecture of this series, and as also the name of the lectures, sort of the course suggests, this is a course which is focusing on theoretical foundations, theoretical concepts, and the reasons why I don't focus on hands-on sort of approach in terms of implementation, R or Python or whatever. I already gave those reasons in lecture 1, but basically, because of various reasons such as time constraints and the fact that the hands-on applications vary a lot, the kind of code that you need to write will vary a lot across applications. That's another reason why I don't think an introductory course one should jump right into hands-on applications. And more importantly, I think it's more important, sort of crucial to understand the theory. And as long as you're not doing something extremely computationally complicated, there are sort of, easily available widespread packages and R and functions which will, train neural networks for you. So it's really not that complicated to implement at least relatively simple neural networks in R. What's more important is to understand the theory, because with widespread sort of popularity and availability of machine learning algorithms, we run the danger that people can tend to sort of overuse it or maybe misuse it and not understand the sort of kind of interpretations that can be validly attached to the coefficients or the results of machine learning algorithms, let's say, and what kind of inference can be applied to it, and what kind of inference cannot be applied. What really these various machine learning algorithms, what are they really trying to achieve? And these are things that we run the danger of not understanding very well because of this, widespread availability of algorithms that one can easily implement. But sort of it's important to understand the theory behind them, at least to some level. Okay. The readings for lecture 3 are these. I follow very closely chapter 6 of the Goodfellow textbook, which is a standard textbook by MIT Press on this deep learning topic for introductory treatments. Um, and a lot of the standard material regarding hidden units and backpropagation and so on, and choice of loss functions, which has to be communicated in an introductory lecture, is based on this textbook, chapter 6. The second one specifically focuses on optimization methods such as stochastic gradient descent and so on, for large-scale neural networks. The third and fourth readings are basically papers in the economic and econometrics as well as macro literature, which make use of neural networks. And this is sort of some recent applications in the economic literature regarding deep neural networks. Okay. We'll definitely discuss the first one by Jesus Fernandez, who is a professor at UPenn. He is, I would argue, one of the best computational economists in the world at this point, and he's made use of deep neural networks recently a lot in solving heterogeneous agent macroeconomic models. Okay. The slides are available on my GitHub link. I've already shared the link in the chat. Okay. Right. So let's just sort of unpack this a bit for people who sort of are completely uninitiated, okay? So as the name suggests, we're talking about deep neural networks. So as with sort of other machine learning algorithms, and we've sort of discussed this in lecture 1, really machine learning algorithms in general and neural networks in particular can be thought of as prediction machines or complicated function approximation methods. And neural networks are no different in that general sense. But they are especially well suited for high dimensional and nonlinear settings, because the kind of models that we covered in lecture 1, for example, lasso and ridge regression, they were essentially linear models, right? Augmented with some sort of penalty term or regularization term to solve the variance bias trade-off. But essentially they were linear models. But when you're trying to model nonlinearities, such as in the case of nonlinear DSE models, right? Or when you are dealing with very high dimensional unstructured data, then neural networks can come very handy. Okay, so they're called networks because we'll see this in a minute. Mathematically, one can think of neural networks essentially as a build from a composition of many functions. Okay, where each function is sort of relatively simple and the complexity of each given function is constrained. But it turns out that when you compose many simple functions, and if you choose them appropriately and so on, and given the problem that you want to solve, a composition of many simple functions can end up being very successful in modeling all kinds of nonlinearity and complexity. And that has proved to be computationally very efficient. And because sort of, neural networks were known like, 4 or 5 decades ago, or even before that. But since the 1990s and so on, so we've been talking about deep neural networks. And this sort of idea of depth and deep learning is what really makes them successful. That you have many networks, so that you combine various neural networks, which is what makes them deep neural networks. And this is essentially, mathematically speaking, a composition of many functions, okay? And when you do this, you're able to get very low number of units per layer, and I'll come to what that means. And then that leads to a sort of great amount of computational advantage. Okay, so I said they're called networks because they are composed of many different functions, okay? they're called deep because the number of layers in the sort of modern deep learning literature can be quite large. Okay. Number of functions essentially that you're composing can be very large. That's why they're called deep. That's the depth dimension. Okay, they're called neuro because essentially there is some kind of analogy going on with sort of neuroscience. And the reason for that is that neurons, just like the hidden units in these sort of neural networks that we'll come to, can also be thought of as mathematically speaking, and that's how they actually work in our biology. And sort of essentially neurons can be thought of as a single given unit, individual neuron can be thought of as a mapping from a vector to a scalar, because it's receiving inputs from various different neurons um, through the synaptic connections in the brain, and then there's an activation value which is determined whether you want to activate the neuron or not, and or it gets inhibited, either inhibited or activated. And so similarly, these sort of hidden units in these neural networks can be thought of as vector to scalar functions, where they are getting inputs from various hidden inputs or units from the last layer, and that determines the activation value. So that's really the analogy. But I should say there at this point that this is only an analogy. One should not think of deep neural networks as essentially models of brain function. Although in some contexts, such as mathematical or computational neuroscience, one can definitely use deep neural networks as models of brain function. But in general, of course, they have applications in economics, lots of industry applications, and so on, computer vision applications, and so on. So they should not be thought of, despite this analogy, they should not be thought of essentially models of brain function, because there is some analogy, but there are also some things that occur in neural network which is not really a good description of what happens with real neurons in the brain. So one should be careful that it's not as if we are literally trying to model brain function, but that we're sort of definitely motivated by that. In fact, some of the hidden units and some of the functions, such as sigmoid functions and other sort of modeling strategy that we use, are actually motivated by what happens in the brain. For example, a softmax function, which I'll come to, can actually has a very good analogy or connection with actual neurons and their workings. But nevertheless, in general, this is only a motivation. And okay, so I just have a picture here. So we have, the biological motivation. I won't spend a lot of time on this, but you have these dendritic connections in the neuron, and get inputs from various, n inputs from various different other neurons. And depending on that, there's an activation value that is determined, which may lead to an electric impulse being passed or not passed, and so on. Okay. Applications abound. So I'm sure you've heard of AlphaGo, which is DeepMind from Google's sort of game, and this was also constructed using a deep neural network. This is sort of one of the poster childs of the success of deep learning. Okay, so I don't have time to go into the detail of how that game was designed, but in 2015, basically, AlphaGo defeated Lee Sedol, who was the world Go champion at that time. And some people have argued that AlphaGo is really the greatest Go player of all time. And by the way, for those of you who don't know, technically speaking, from a sort of permutational and combinatorial perspective, Go is actually even more complicated than chess. And the number of arrangements that you could have on the board are actually more than the atoms in the observable universe, which sort of mind-boggling complexity. And so sort of previous algorithms, which were not as efficient neural networks, were not able to deal with this sort of combinatorial explosion of this problem, but neural networks were able to solve it. Okay. The other applications in speech recognition, object recognition especially is very important application neural networks, such as facial recognition, computer vision in general. Of course, in finance and economic context, you can use it for all kinds of prediction problems, especially those that are high dimensional and non-linear. And when you don't have any a priori idea about what kind of concrete non-linear form of non-linearity that you should choose. If you don't know that, then you should use a neural network, because they're able to learn very general forms of non-linear functions, very complicated non-linearities, and they can learn them. You don't have to specify the non-linearity form of the non-linearity. So that is the use in prediction of stock prices and other prediction problems, prediction such as they've been used to predict inflation by Nakamura and Steinson in Colombia, I suppose, in the recent past. Yes. And so we won't be covering recurrent networks, but because they have backward connections, and this lecture is focused on deep feed-forward neural networks, in which information is only sort of flowing forwards from the input to the output vector. But we also have recurrent networks that is used in deep learning, and especially this is very useful for sort of natural language processing and speech translation, speech recognition, syntactic parsing, and computational linguistics. In fact, lecture 4, which is tomorrow, is about computational linguistics, but we won't discuss recurrent networks. But recurrent neural networks are used in conjunction with other tools of computational linguistics that we'll cover tomorrow. Okay, economic applications, they're used in high dimensional econometrics, high dimensional forecasting. Computational linguistics is being used a lot in empirical macro, especially, and also other fields nowadays. And you can use neural networks to train these algorithms. And also, they've been used recently by people like Jesus Fernandez and other people in sort of solving nonlinear DSE models, which is sort of really interesting, I thought, as a student of macroeconomics, because they have these sort of policy functions, which we usually solve using sort of dynamic programming techniques and things like value function iteration or perturbation methods and Chebyshev polynomials and that kind of thing. But sort of they have recently come up with a new method for solving these DSE models using neural networks as a function approximation method, which can approximate the policy functions in the model, especially in a nonlinear model. Okay, in which other standard methods of dynamic programming fail because of the fact that the cross-sectional distribution of the wealth is infinite dimensional. But we'll come to that. Okay. This is just an example to motivate what neural networks are really doing. And I'll come back to this after this slide. Okay. So just like any other optimized machine learning algorithm, right? There are some standard choices that have to be made. And in that sense, neural networks share some features with other machine learning algorithms. So for example, you of course need to choose a loss function. For example, whether you'll choose a mean squared error loss function or some other measure of the cross entropy between the data and the distribution that you want to minimize, maximum likelihood, and so on. And of course, you want to use the optimizer and so on. But there are some new choices regarding network architecture and the form of the hidden and output units that you need to make when you're trying to train a neural network. Okay. And just like other linear models, we use gradient descent based algorithms to solve, to find the parameters, to optimize the parameters, which helps us pin down the distribution of the data. But there are some sort of peculiarities that occur because it's very hard to compute gradients for neural networks, unlike linear models. And we use techniques such as back propagation and stochastic gradient descent, which mainly have a computational value, and they increase our computational efficiency, which becomes relevant in the case of neural networks because they're high dimensional models. And just like other machine learning algorithms, as we discussed as lecture 1, we have regularization. And regularization is basically trying to solve the variance bias trade-off that we discussed in lecture 1. And you can augment the loss function, even in the case of a neural network, with penalty terms and so on. Okay. So mathematically, as I said, oh, by the way, deep feed-forward networks are also called multi-layered perceptrons. That's just a term that's also interchangeably used for it. Okay, so as the name suggests, these are deep feed-forward networks, which is a special kind of deep neural network. And this is basically what we'll be covering. We won't cover recurrent networks. And convolutional networks, which we won't cover, but they're also a special kind of deep feed-forward network. So you need to understand this in order to understand convolutional networks and so on. Okay. So what you're trying to do is to learn some unknown function, right? We have data on what are called features in the ML literature, but in general, in econometrics, we call them sort of independent variables, or covariates or control variables, whatever you want to call them. We have data on some X, and we want to predict some outcome y. Just like in any other ML sort of context, we want to solve a prediction problem. We want to learn a generalizable structure from the training data so that we can predict the value of the outcome y given some new data x, which is not part of our training data. Okay. So yeah. So this function f star is what we want to learn. That's a true function that exists out there that we want to learn, which maps the inputs to the outputs. And the way an f without the f star, just f, is basically the function approximator that the neural network is trying to implement. And our objective is obviously to get, to minimize the distance between f and f star, given whatever measure of distance that we've chosen, such as mean squared error, for example, or maximum likelihood and so on, which is the negative of the log of the likelihood and so on. Right. So as I said, these neural networks basically are trying to come up with a function approximator f. But this function approximator f is in turn can be expressed as a composition of n different functions, right? So rather than applying one complicated sort of nonlinear function, which will be very hard to learn for us, what we do is that we apply a series of functions, f1, f2, all the way to fn, and n is the depth of the neural network. If n is higher, we say we have a deeper neural network, or basically n is the depth of the neural network. Okay. And there are n sort of layers. These are called hidden layers as well. The number of functions that we are composing together is a number of hidden layers. Okay. And this is what we mean by deep neural networks, because if n is very high, then we have a lot of depth in the neural network. Then we're dealing with a very deep neural network. Okay. So each one of these functions, they're not linear, of course, because a composition of n linear functions obviously leads to just a linear function. So, they will be nonlinear, and they'll have particular kinds of relatively simple nonlinearities. But when we compose these together, along with some sort of optimization routines for figuring out the parameters which show up in all of these hidden layers and output layer, we will basically be able to model very complicated forms of nonlinearity, which we cannot model directly because we have no idea how to do that. But when we compose all of these functions together, we can do this. Okay. Right. So all these layers like F1, F2, all the way to Fn, these are hidden layers, right? You don't have data on them. You only have data on X and Y, and then you apply a transformation F1 on X, and then you apply F2 on the outcome of that and so on. But sort of the output F1 of X, which is going to be the input for the function F2 and so on, these are sort of called hidden layers or hidden units. And we don't have data on these intermediate layers. We only have data on X and Y. And that is what we're interested in. We want to predict y given data on x. And the way we design these intermediate layers has to be determined by our learning algorithm. And that is where the algorithm has freedom to sort of, learn these hidden layers in the way which leads to the best optimal prediction for y. Okay. So for example, I won't discuss the other examples, but it has been used in lots of object recognition, facial recognition kind of applications, right? So for example, it's very complicated to learn faces, right? Because there are lots of different dimensions. It's a very high dimensional thing. You have to consider lots of things, like whether the same person, if it doesn't have facial hair versus if he has facial hair, will look very different. And as humans, we can do this sort of, object recognition sort of instantaneously and sort of, but effortlessly. But it's actually turned out to be a pretty darn hard problem to solve in computer vision. And so it's very complicated because it's a very high dimensional map and non-linear kind of mapping from the inputs, which in this case will be sort of pixel configurations to the output, which is sort of faces. It's very complicated to learn this function. We don't have any ideas what sort of function this should be a priori. And so what neural networks do is sort of decompose the problem into simpler steps. And in this picture, you only have one layer, but like we have lots of layers, right? So for example, the first layer could only focus on learning whether you have an eye or not in the picture. And if you have something which resembles like an eye, which was basically going to be a particular combination of pixel configurations, which translates to what looks like an eye, right? Or there could be other layers, which could be so-called nose detectors, or cheek detectors or chin detectors and so on, and or hair detectors. And once you have all of these layers, and each one of them is trying to detect a particular relatively simple kind of feature of the input space. And when you compose them together, And because there are connections between all of these hidden layers, a particular pattern of connections that gets triggered by a given input could trigger the output as associating very high probability to the outcome that you have a face over here, or the face of a particular person, if you want to carry out very specialized facial recognition, which is very complicated to do, and so on. And of course, you could apply this on recognition of other objects. Okay. And in terms of the sort of flow representation, um, this is how we think about neural networks, right? There's an input layer, which is the yellow layer, and in this case, you only have 3 inputs, and then you have 2 hidden layers in this particular graph, and there is and sort of the pattern of interconnections that exists between these hidden layers will be determined by various parameters in the model that I'll come to. And ultimately, given any particular input, once we've trained the neural network on some inputs, and we try to predict the output with a new input, which was not part of our training data, which was part of our test data. And again, we discussed these terminologies in lecture 1. So we will be able to predict an output for something completely new. So for example, we will train the facial recognition network on some faces, right? But then in the future, you may see a completely different face, which was never part of the training data. But if neural networks are successful, they'll be able to detect that this also is a face, and they'll be able to generalize it. And okay, and it's sort of mind-boggling because we do this effortlessly, and none of us has actually seen the infinitely many different possible faces that could exist out there. But we recognize a face whenever we see it, and it might seem trivial to us because millions of years of evolution has done this wonder on our brains and visual systems. But it's actually quite complicated to sort of to sort of model computers to do this. Okay. So the problem is that if you just have a linear model, right? If you don't have a neural network, and if you just have inputs X, and if you just take an affine combination, apply affine transformation, and these are, so by the way, just as in all of mathematics, when I use boldface letters, these are for vectors and matrices, and so when I don't use boldface letters, these are for constants, right? So if you have simply a linear model, obviously that is not going to be able to capture the interactions between various inputs, and it will not be able to model non-linearities. So the general idea is that in neural networks is that we continue to work with a linear model, but we add a hidden layer, okay? And the hidden layer is going to have some sort of non-linearity. It's going to apply a non-linear transformation phi, okay, on this input vector X, right? And yes, and once we apply this nonlinear transformation, we get some output in vector form. And then we apply the linear function f, which is just taking, just a function of the form f, which is written in the first line. It is just an affine transformation of the inputs from the nonlinear transformation. So we are applying a linear transformation in the second layer, but in the hidden layer in the middle, we are applying a nonlinear transformation. And what this does is that it sort of transforms the sort of feature space or the input space because of the nonlinear transformation. And once we've transformed it, it becomes amenable to sort of learning by a linear function. Initially, it was not amenable. It was not possible to learn it through a linear mapping. But once we perform these nonlinear transformations, we can learn the output, or learn this function by simply a linear sort of affine kind of function. Now, obviously, the whole point is that how will you choose this phi, right? So, I mean, this is a very general treatment, and you need not use neural networks to sort of estimate this phi, but we're going to, I mean, that's what we're going to do. We're going to learn phi using deep learning. But, some of the alternatives, historical sort of, artificial intelligence kind of literature was to, use a very generic infinite dimensional kind of phi, or you could learn it through decades of specialized training and human effort, which is dedicated on a specific task. And these people are trying to manually engineer what phi should look like. Now, both of these approaches have their own advantages, but also disadvantages. And deep learning basically can be thought of as trying to combine the advantages of both of these approaches, which is why it's really successful. The second approach is very specific. It's too specialized. It's not general. And also it's very time consuming. it will take perhaps, decades of human effort, a lot of human resources for us to really learn what sort of nonlinear mapping is relevant for various contexts. And this will be highly context dependent. So it will be very specialized and it will take a lot of time and effort. On the other hand, if you try to use sort of, mathematical theory to come up with an infinite dimensional kind of generic phi, that's too general. Um, um, and sort of it's really hard to pin down what sort of parameters you should choose in a certain context. We have very not general function which can model all kinds of nonlinearity, but what kind of parameters you should choose for this generic phi in a particular context is not going to be obvious at all, right? But using deep learning, we keep the structure relatively general because they can model all kinds of complicated nonlinearities. But we optimally learn parameters theta using the deep learning algorithm, gradient descent based learning, not manually. And so we combine the sort of generalism of the generic phi with the sort of benefits of the specialization of the manual engineering when we use deep learning. Okay. So this is an example, a standard sort of textbook example, which is, I think, very useful, even though it's a very simple example, but it helps illustrate what neural networks are really trying to do. So this is known as the exclusive OR function. It's a very simple function. It's just a function which just takes a value of 1. It takes 2 inputs. So it's a function from R2 to R1. That's the first thing. And it takes 2 inputs, which could either be 1 or 0. It takes a pair of binary values as inputs. If exactly one of the 2 binary values is equal to 1, then it takes an output of 1. Otherwise, it just returns 0. So if you have 1, 0 or 0, 1, in these inputs, it will give an output of 1. Otherwise, for 1, 1 and 0, 0, it's going to give you, for the other 2 possibilities, an output of 0. This is known as the exclusive OR function. It's a very standard example that's used to motivate neural networks. Of course, in practice, we don't know what the F star function is. Of course, that's the whole point. Otherwise, we'll just, we don't need neural networks to learn F star. But this is sort of an example in theory. If you know what F star is, can you train a neural network to sort of to learn F star? Because in this case, it's very easy to compare the performance, evaluate the performance of neural network because we know what F star is, and we can compare F with F star. So if F star is this exclusive OR function, we can train. It turns out we can add, even in this case, only one hidden layer is needed, and you can adapt the parameters and you can try to learn this function. In this case, actually, you can learn it exactly. So we have these 4 data points, right? 0, 0, 0, 1, 1, 0, and 1, 1 in the training set. And in general, of course, we want to generalize from the training data. But in this particular special theoretical sort of plain vanilla case, there is no variance bias trade-off. There is no statistical generalization. It's just that you want to find a function which exactly fits the data, which gives you exactly the right answer, which should be, the output should be 0, should be 1 for the second and third inputs, and it should be 0 for the first and fourth inputs. And you want to basically learn this F star function exactly. And of course, you need some measure of error and loss if you want to evaluate the performance of the prediction. And even though mean square error is sort of not really used that commonly in neural networks, but here we just use this for simplification. The problem is that if you look at the original space, right, you have 0, 0, 1, 0, 1, 0, 1, and 1, 1. This is sort of a there's a non-linearity in this function, even though it's a very simple function. But there's a non-linearity in this function. And it's not possible for you to learn this function, even though it's a very simple function. But it has a simple form of non-linearity. And it's not possible for you to learn this function using simply a linear model. So what we do is that we just use a deep feed-forward network with one hidden layer, okay? That's the simplest thing we could do. This is not really a deep neural network, just has one. The depth is just 1 because it just has one hidden layer, right? So what we do is that initially we apply a sort of affine linear kind of transformation on X, which is the input. That's the first sort of, this is called the first function, F1 that we're applying. And then we sort of apply, then we sort of use G, which is called an activation function. And this is where the action lies, because otherwise we just have, two F1 and F2 are just affine transformations. F2 is applied on H. F2 applies an affine transformation on H and returns a scalar, which should be 1 or 0 in our case. And F1 is just also another affine transformation, which returns a vector and not a scalar. but it's an affine transformation which is applied on the initial input space X, which is this space on the left. Okay. But after applying F1, which gives us, capital W transpose X plus C, we apply this function G to get H, and then we apply F2 on H. So this G is a nonlinear function. It's not linear, right? Because if G was also linear, then you just have a composition of three functions from X to Y, and that just gives you linear functions. You can't learn the nonlinearity. Now, there are various choices in the machine learning literature, in the deep learning literature, for what this activation function should be, and it depends on the context. But a sort of default choice nowadays, this was not the case in the 1990s, but this is considered one of the biggest milestones actually in the recent deep learning literature, is to use what is known as a ReLU activation function. Now, the ReLU activation function, the full form is rectified linear unit, is a piecewise linear function which is very simple, and actually just has this form. So it just returns 0 when you have a negative input, and otherwise it's just an identity function, right? So it's a very simple function. It's very trivial to compute computationally as well, and it's sort of theoretically also a very simple idea. This is a piecewise linear, piecewise differentiable function which takes a value of 0 if z is negative, z is the input, and it is just the identity function g of z equals z if you have a positive value of z. This is not differentiable at 0 because it has a kink, but it's differentiable everywhere else. Okay, and it's piecewise linear and so on. So it's piecewise linear, so it really behaves like a linear function, towards the right of 0, let's say. But otherwise, but it also has a simple form of non-linearity. If you look at the function as a whole, right, it looks very much like a sigmoid function. Well, at least some subset of the sigmoid function. And it has this kind of non-linearity, a kind of right parabola, parabola type behavior. Not really, but like approximately. But it's also very linear, and it models simple form non-linearity at the same time, but it also behaves very much like a linear function throughout most of its domain. So it's very convenient to deal with computationally, and it solves the vanishing gradient problem of the sigmoid function, which was the previous choice of G that was used in the literature. And I'll come to what this problem was. But basically, in the modern literature, we tend to use this ReLU activation function as a default choice. And we're applying this, remember, on W transpose X plus C, and G is a ReLU function. So we just have max of 0 and this vector, okay? And this is going to be applied piecewise on the outcome of the function F1. And then once we've done that, we just get H, because that is what G gives us. G is a hidden layer, and from this hidden layer, H is a hidden layer, and then from the hidden layer H, we just go from that, and we apply F2 then, which is another affine transformation, which goes from Rn to R1, and so on. And ultimately, we just get a scalar. So it turns out if you do this kind of thing, and of course, this is a theoretical example, and in this case, there exist choices of these, parameters, which are W, C, small w, and B, right? Because all of these coefficients that show up in these functions, G is, we know what G is. There is no new parameter being introduced by the ReLU function, right? Which is another benefit actually that it has, is actually doesn't introduce any new parameter. We just have these weight matrices, which are called weight matrices, and then you have these so-called bias terms, B and C and so on, which we would call intercepts in economics, but in the machine learning literature, these are called biases, because the bias to estimate up or downwards. So these are the 4 parameters you need to estimate, but this is just a theoretical example. So in practice, we would estimate these using gradient-based learning. But in this particular hypothetical theoretical example, if it turns out, and you can verify this on your own, this is a standard textbook example. If you choose these particular values, B0 and vector W is 1 minus 2 and C is 0 minus 1, and you choose the sort of simply the sort of this is 1 1 1 kind of matrix for W. It turns out if you do this, and then if you use these values for W, C, small w, and B, and so on, and then you figure out what the prediction will be, right? Given any x, where x actually, as you said, are 2-dimensional points, and the 4 possible values of x, 0, 0, 0, 1, 1, 0, and 1, 1. These are what x is. X is a vector, which is a 2-dimensional vector, okay? and that is your input. And once you choose these, but use these particular values for small w and capital W and so on, and C and B, and if you just do the calculation on your own, it's very simple. You can do this by hand. You will realize that in that case, you perfectly learn the exclusive order function, so that whenever the input is 0, 0, the output of F, which is W transpose max of this plus B, this whole thing, which is a composition of two functions, F1 and F2, where F2 is being applied on G. And if you apply this this kind of neural network actually with one hidden layer, in which you already know what the parameters are, we're not learning it in this particular case. And once you apply this and calculate the predictions for all of these 4 different input points, you'll get the prediction that when X is 0, 0, you get 0 as an output, which is exactly what you should get. And when the input is 1, 1, the output is 0 again, because remember the exclusive OR function should return 1 only when exactly one of the two binary values is equal to 1, which is what happens only in the second and third cases. This is, by the way, a typo. This should be comma, not 0.1. Okay, so only in the second or third cases it will return 1, otherwise it will return 0. And in this case, loss is actually 0 because you're able to perfectly learn it, right? You don't need to actually minimize anything. This is actually perfectly 0. But of course, in practice, this is not how it works. But that is sort of really trying to illustrate the main point of this is that you have this original space, right? And that was non-linear. And it was not possible for a linear model to learn this, even, apparently very simple function. But if you use a neural network with one hidden layer and you transform the X space into the new space H, which is increasing in X1 and decreasing in X2 dimension, this can be learned by an affine transformation, which is applied on H, which is not the case on the original space. So machine learning in general, this is what it's trying to do. Neural networks, especially, not machine learning, neural networks are trying to do this in general. They're trying to transform this original space of inputs by applying these sort of composition of functions and nonlinear transformations. And they're trying to transform the original space into a new space, which is called the learned space, which becomes amenable to a sort of linear model. Of course, in practice, you have lots of you could have billions of model parameters and so on. Of course, you're not going to be able to get 0 error. And of course, in practice, you try to minimize the error, produce as little error as possible, but not exactly 0. And in order to do that, in this case, this is a standard example, so we know what the parameters are. And we just reverse engineer these parameters, solving the equations and solving some, matrix equations and so on. It's not very hard. But in general, of course, that's not how it works. And we will need to use some sort of gradient descent-based algorithm to learn these parameters. And once we've learned these parameters, we have the predictions. And then those predictions will produce ideally a very low error if we're able to do the optimization properly. And not exactly 0, of course. But that's sort of the general idea. And so as I said, they're trained using gradient-based learning. So this is sort of from a fundamental perspective, not very different from the kind of gradient-based learning that is applied on linear models, for example. But it's just that calculating the gradients is sort of complicated because of the dimensionality problem in the neural networks. And otherwise, sort of is fundamentally the same as any other kind of, for example, applying any other kind of gradient-based optimization routine for, let's say, solving the ridge regression problem and so on. But otherwise, sort of the main difference is that not theoretical but practical, but computational. So computing the gradient is very complicated, and that's why we need some new tools and some new algorithms, and which are known mainly backpropagation and stochastic gradient descent. And I'll come to this. These are commonly used because they help you compute the sort of gradient as well as perform the gradient-based learning algorithm, implement the gradient-based learning algorithm in a computationally efficient way. And okay. So next, we sort of, as I already said, just like any other machine learning kind of algorithm, you need to make some standard choices here. So for example, if you have some, the conditional distribution of the data, the sort of y variable conditional on the x variables, the features, as they're called in the machine learning literature, and some parameterized by some theta. So there are various choices that one could use for the loss function, right? Which is just some criterion function. Just like in OLS, we're trying to minimize the sum of squared residuals. We need some sort of criterion function, right, which we want to minimize using gradient descent type algorithms. And you could have lots of choices like mean square error and lots of other choices, um, but and there is no one answer to this. But sort of often, and in many contexts, actually, this is the appropriate loss function to use in the context of neural networks, not necessarily in any other machine learning context. But in the context of neural networks, often we tend to take the maximum likelihood approach, where we write down the likelihood function of the data, the y condition on the parameters theta and x, and we try to maximize the log of the likelihood, which is just a monotonic transformation on the likelihood, and which is equivalent to minimizing the negative of the log likelihood. So the loss function, because we want to minimize the loss, not maximizes, it will be the negative of the log like expected value of the log likelihood with respect to the joint distribution of the data, um, conditional of the observations x. Now, I'll come to why we use this, and the log likelihood, the negative log likelihood, is also related to the some sort of measure of distance, which is the cross entropy between the data and the empirical, and the data and the model, and the distribution of the model. But that's not important for us at this point. But of course, in practice, just as we discussed in lecture one, this loss function, L of theta will be sort of, augmented with, it'll have some sort of penalty term because we want to solve the sort of a variance bias trade-off. Either we'll have a sort of L1 penalty, which is when you get the lasso, or we have the L2 penalty in which you get the ridge regression, in which you have a lambda, a tuning parameter, and times the sum of squared coefficients and so on. So you have these sort of regularization terms even in neural networks. So because just like any other machine learning algorithm, neural networks run the risk of overfitting, and so you want to avoid that. Especially neural networks are very sort of flexible, technologies, and they can learn all kinds of functions. And so you have to be careful. You want to tie the hands of of this algorithm. You don't want to, give the algorithm full freedom to estimate some nonlinear function trying to match the data, because then it will tend to overfit, and then overfitting is not what you need, because your whole objective is to generalize and to predict in novel contexts that you haven't seen before. That is what makes the algorithm useful. So typically in practice we will have some kind of regularization term being added to this as well. Right. Now, the problem is, I'll come to this when I discuss output units, but there is a so-called vanishing gradient problem in this neural network literature. And what happens is that you have these sigmoid type of functions that will saturate, for example, if you have this kind of sigmoid kind of function in red, it will sort of saturate for very high, large values of inputs towards one. The gradient will sort of, become really flattened. Similarly, for very large negative values, it sort of saturates around zero, and is sort of this S-shaped logistic kind of sigmoidal function has this property that it saturates around zero and flattens when inputs are either large and negative or large and positive. And when you have this kind of saturation of the gradient, it's well known that gradient-based learning will sort of fail, because remember, if you know this from your previous studies, gradient-based learning is going to work well when you have a steep gradient, because that is going to give us information regarding where we should move next in order to update the parameters. But if you have the saturation of the gradient, you won't be able to learn the parameters really well, and that creates a problem and failure of these. That was actually a major problem, and so what the log likelihood function does beautifully is sort of is undoes the exponentiation that is often shows up. So in a sigmoid function, you have the exponential function which just shows up, right? And in the function, but that's how it's defined. Similarly, you have the softmax function, which I'll come to, and that's what we use when we have multinomial outputs. So we have a lot of output, what are called output units. I'll come to those in a minute, which have the exponential form, right? So in the distribution, in the likelihood. So when you take the log likelihood, the logarithm tends to sort of undo this exponentiation, which is sort of built in these softmax and sigmoid functions, which I'll describe in a minute. And so the log likelihood is a beautiful choice because it sort of undoes this exponentiation. And this exponentiation was the source of the saturation, right? So for example, if you have exponential of z and you take the log of that, you just get z. And z is not going to saturate when you have very large value of z. But exponential of z is going to saturate when you have very large negative values towards 0. So this sort of the log likelihood is a very natural choice because it helps avoid, you solve the vanishing gradient problem basically, which inhibits your gradient learning. And because eventually you'll take the gradient of the loss function, right? L of theta. That's what you'll learn. The gradient-based learning is based on evaluating numerically the gradient of the loss function. And once you take the log likelihood, you end up undoing the exponentiation, which often shows up in many output units. And that helps you avoid the the vanishing gradient problem, which inhibits your gradient learning. So that's why often the maximum likelihood, the negative log likelihood, is a very natural choice. In fact, it may be the only choice that works, especially when you have sigmoid functions. It's like a natural recommendation, in fact, that you should use the maximum likelihood based loss function. Okay. Because if you use a mean squared error loss function, you're not going to undo the exponentiation and you will have the vanishing gradient problem. Okay. So if you remember, you had these various sort of layers, right? Hidden layers in the flow representation that you saw, and output layers and so on, right? And so in neural networks, we have to choose uh, what kind of what is known as the output unit choice and the hidden unit choice. So we have output units, which is the final sort of layer, right? Which maps from, for example, in this case, the sort of F2 function was basically the choice of the output unit, because H was a hidden layer and F2 was basically mapping, ultimately giving us the output prediction, right? So F2 is basically the choice of F2 in this simple learning exclusive OR function example will be the choice of the hidden unit, the output unit. And the choice of the hidden unit will be the choice of G, or which is also known as the activation function, which gives us a hidden layer. And that is the choice of the hidden unit or the choice of the activation function, which is G. On the other hand, the choice of the output unit, which is actually linear in this case, because it's just applying an affine function on W transpose H plus P, is F2. So we need to make these choices, right? What kind of activation functions you should choose, what kind of output units you should choose, and so on. So these choices have to be made for neural networks. And of course, um, the choice of the output unit is closely related to the choice of the cost function or loss function, because you're measuring the loss function in terms of output units. It's a probability of y. So for example, if y is binary, if you're trying to solve a classification problem which just says you want to train a neural network to determine whether the object that you see in front of you is a face or not, just a 1-0 binary outcome, if that's what you want to predict, the probability that it's a face, for example, then you have a binary outcome y. In that case, we tend to use the sort of sigmoid function, because for those of you who know this, this is very basic. The sigmoid function, as you can see in this graph, is always going to return a value between 0 and 1. So it's a very natural choice to use if you want to deal with a Bernoulli kind of model in which just have a binary prediction outcome. Okay, because if you apply the sigmoid function on any input, which could take values from negative infinity to infinity, and it will give you always a number which is somewhere between 0 and 1, strictly between 0 and 1, and that is why it's the natural choice when you have to model probabilities. Okay, when you have a binary model. Okay. So yeah, so if you have a Bernoulli distribution, then what you're trying to learn is just the probability of success y equals 1 condition on the data. And a common choice in this context would be to the choice of output unit I'm talking about right now. I'm not talking about hidden units. I'm talking about output units right now, right? Which is applying this ultimate final layer on the last hidden layer H to get to the prediction, right? And since we want to predict a binary outcome, we will choose a sigmoidal output unit, where sigma of this W transpose H plus P, that is the affine transformation that we're applying on H. And then we are applying sigma, where sigma is a sigmoidal function, and that returns a value between 0 and 1. And that is going to be your prediction of the probability of, let's say, when you have a face in front of you or not, and so on. But we have to be careful that, as I said, when you use sigma, you have the vanishing gradient problem because the gradients tend to vanish towards very large input values and so on. And this inhibits the gradient-based learning. So when you use sigmoidal output units, you must use a maximum likelihood-based where you take the logarithmize the exponential terms that show up in the definition of the sigmoidal function, as you can see over here, and they will sort of end up offsetting it and solving the vanishing gradient problem. On the other hand, an even more sort of easier choice would be simply to use linear output units, which is what we did in the exclusive OR function example that we did. In this exclusive OR function that we did, F2, remember, was not sigmoidal. We didn't have any sigmoid function over here, right? We just had a sort of affine or linear kind of function, which was our hidden choice of the hidden unit, output unit, or the final layer, F2. And this is not a nonlinear function. This is not a sigmoidal function, because here we weren't trying to predict the probabilities, right? We were literally trying to get a number 1 when you have a second or third case, and a number 0 when you have the first or fourth case. So we're not trying to predict probabilities. When you have, this is known as a regression problem. So if you're solving a sort of regression problem, then, or if you have a continuous sort of y, then you could use linear units, right? Which is simply a linear function A that is applied on H, W transpose H plus P. Simply linear output unit. And they have some nice properties because they are convenient and sort of optimization, and they don't saturate because they don't have this S-shaped kind of behavior. So they don't have a vanishing gradient problem and so on. But of course, if you want to predict a probability, then you can't use a linear function, right? Because there's no guarantee that the linear function will give you a value between 0 and 1. So you can't use a linear kind of output unit in that case, and you'll have to use a sigmoidal function. But when you use a sigmoidal function, you have the vanishing gradient problem. So one has to be careful to make sure that one sort of undoes this kind of exponentiation in the sigma function by using the log likelihood as the basis of the loss function. Okay. Another popular choice, and I'll cover only these three because they are the most commonly used ones, many others, of course, is what is known as softmax output units. So when you want to represent a probability distribution, which is multinomial, right, rather than binomial, and which you just have a probability distribution over n possible values, where these n probabilities have to sum up to 1, right? Rather than just zero binomial kind of sort of Bernoulli kind of thing. So we need to produce some prediction in this case such that each one of these, there are two conditions. Each one of these y hat I, where I goes from 1 to n, should be a probability, which means it should be a number between 0 and 1. And it should also be the case, the second condition is that the sum of those probabilities should sum to 1. So that this should lie in what is known as the n-dimensional simplex, for those of you who are familiar with economic theory. So what we do in this case is apply what is known as a softmax function. What we do is that sort of we have H, right? H, remember, was the last hidden layer. There could be multiple hidden layers. So H is the last hidden layer because we're trying to talk about output units right now. So from H, the last hidden layer, to the output unit of the neural network. So the last function in this sequence of compositions, right? The nth function, essentially, in the notation that we used before. So this first we apply this sort of affine transformation, W transpose H plus P, which we also applied in the sigmoidal case before we take the sigma function, the sigmoidal function. But then we cannot apply the sigmoidal function, of course, because the sigmoidal function, of course, if you apply it element-wise, it will ensure that each one of these is a probability. Each one of the zi's is a probability, but it's not going to show that those sum up to 1, right? Because it could get 0.9 and 0.7, which of course don't sum to 1, and in the first two elements they could be bigger than 1. So you can't use a sigmoidal function. You use what is known as a softmax function. So what we do is that we exponentiate the input zi. We apply it element-wise on the vector z. Z is a vector, which is why it's in bold. It has n dimensions, let's say. So if you're trying to apply the softmax function element-wise, you take the exponential of zi, the input, and then you divide by that as normalization factor, which is the sum of the exponentials from j1 to jn of all the z's in this vector. And if you sum all them up, you'll realize you just get the sum of the exponential in both numerator and denominator, which is just equal to 1. So the probabilities will sum to 1 if you do this kind of normalization. And the reason why we're taking the exponential is that z, which is an affine transformation on h, is our measure. We're trying to model it in such a way that we're interpreting z as the log of the unnormalized probability. Of course, these don't sum to 1, which is why this is unnormalized. They don't sum to 1. But whatever input you're getting from W transpose H plus B, we are interpreting that as also a probability, not just a probability, but a log of the unnormalized probability. That's how we interpret it. And then we exponentiate it to sort of undo the log. And then we sort of, so that we actually get, and then we also normalize it. Then that's when you're going to get P rather than P tilde, which is sort of the normalized probabilities. And the softmax terms will sum to 1. So, for example, if you have n different, let's say you're trying to solve a digit recognition problem, right? 1, 2, 3, 4, 5, 6, 7, 8, 9. You have 10 digits to recognize, and you want to assign probabilities where n will be 10 in that case in this sort of 10-dimensional simplex, which should sum to 1. And it should tell you the probability with which the algorithm or the machine or the deep neural network should output the probability n probabilities, where each of the probability is a probability that you've observed a particular digit. So, for example, if I write the number 7 a very kind of almost undecipherable way, but somewhat decipherable way because of my handwriting is bad, handwritten number 7, and a very well trained and successful neural network will tell me that this is number 7 with, let's say, 90% probability, and the rest are going to sum to 10%. So that's the kind of output they're talking about when we're trying to use a softmax function. Okay. Again, the softmax, as you see, has these exponential terms, right? Just like the sigmoidal function had these exponential terms. And so the beautiful thing about this is that you have these exponential terms. And when you take the log likelihood, as I said already, then you undo this exponential term. You get Zi itself, which is not going to saturate. But the exponential terms will saturate. And you have the saturation problem, which is going to inhibit your learning problem. And whenever you have exponentials showing up in the output unit, you should use a log likelihood so that you undo that exponentiation and you solve the vanishing gradient or the saturation problem. Okay, which is particularly acute for the exponential type functions. Okay, and this will prevent your learning. Now we talk about hidden units next, right? We also had G, right? This we were talking about the last sort of output unit right now, and the choice of what sort of output unit to use was motivated by the problem at hand, right? So if you're trying to solve a problem in which you just want to predict the probability of success 1, 0, a binary thing, then you use a sigmoidal function, but make sure to use the log likelihood to undo the exponentiation. Similarly, use a softmax when we're trying to predict n different probabilities, a multinomial distribution. And we use the linear output units when we're just solving a regression problem, which we just have to predict some continuous variable, not a probability. But so we had some kind of motivation, right? We knew what sort of output unit we should use because we know what sort of problem we want to solve because we have data on the output variable y, and we know what sort of thing we're trying to predict, right? Whether it's a probability or continuous variable. But then we also have to make the choice of G, right? It's hidden units, which I talked about, the ReLU function and so on. This is not a very natural choice because we don't have data on these hidden intermediate layers, and that's where the sort of deep neural network is really a black box because the way it sort of is learning through all these hidden layers, we don't completely understand it even at this point, actually, and it's really a black box. We just know that certain kind of we have some theoretical guarantees in some cases, although the theory of sort of machine learning is really still in its infancy. But we have some theoretical guarantees. And we know that certain functions work very well in practice and certain choices work well in other contexts. But really, we don't have a lot of good theoretical sort of guarantees on what sort of hidden units to use. So in the 1990s, so the logistic or the sigmoid function was used as a hidden unit. Just like we discussed that we should use the sigmoid function for the output unit, right? When you were trying to predict a probability. But even if you're not working with with probabilities, you could, and it was used in the 1990s, you could use a logistic function as a hidden unit, right? Yes, it's going to output some number between 0 and 1, but then that is in the hidden layer. So you're not trying to predict, that's not the output layer. So you could use the logistic function in the hidden sort of layers in the choice of the hidden unit, even if you're not solving a probability kind of problem, even if you're just solving a regression problem. But of course, you would not use sigmoid function in the output layer in that case if you're not solving a probability problem. But so in the 1990s, sort of the standard choice for this activation function G, remember, which was a form of nonlinearity, was the sigmoid function. And in the sort of late 90s to 2000s, we had a hyperbolic tangent function, which sort of, so So this sort of, I just have this plot of the sort of sigmoid function, which is all we already saw in the previous diagram as well. It just takes a value between 0 and 1 always for all the inputs from negative infinity to infinity. And on the other hand, that the hyperbolic tangent is very similar. It has similar kind of S shape, a slightly different curvature, slightly steeper towards the middle of the domain, but it takes values between -1 and 1. Okay, that's the only difference. So this became the sort of choice, the hyperbolic tangent, in the late 90s, 2000s, because it was shown that in practice it tends to work better than the sigmoid function. Okay, and why it actually works better is sort of not completely understood, and it's quite complicated. But often this is the case in machine learning. It's a black box. We don't really deeply understand why machine learning works actually at this point. Um, um, but we know that it works really well. Okay. But nowadays, this is no longer the case. So nowadays we use what are known as rectified linear units as a default choice. Now, to be fair, there are some contexts, such as in the case of recurrent neural networks, which have backward as well as forward connections. We won't cover them, but there are reasons why the sort of ReLU function is not actually valid in that case. So we continue to use a sort of sigmoid kind of, or actually hyperbolic tangent in that case, kind of hidden unit. But otherwise, for most sort of machine learning applications, especially in the convolutional networks case and in the deep feed forward network case, which we are covering, ReLU is a sort of standard default choice in the contemporary ML literature. Why? Because it solves the vanishing gradient problem. I already told you what ReLU function is. It's just a stepwise linear function, which just inputs 0 if you are inputting a negative value of z, and it takes the output of simply the identity function if you have a positive value of 0 and so on. And it models a simple form of nonlinearity. It's very easy to compute and deal with. It is piecewise linear and piecewise differentiable. Okay. Um, it's not differentiable at 0, but it's differentiable everywhere else. And so what we do is that, in this hidden layer and the hidden unit, we use W transpose X plus B. We have some transformation that we apply on the initial input X, and then we apply this G, this nonlinear ReLU function, right? Um, Now, of course, if you're talking about a deep neural network, then there could be 10, 15, 20 hidden layers, right? You're composing various functions. That's why this is called deep neural networks. Then all of the functions typically will be the same, even though in principle you could use different functions G at different sort of hidden layers. But in practice, almost always we tend to use the same activation function G everywhere. So if you're using ReLU, you will use a sequence of various compositions of ReLUs being applied successively, and eventually when you use the output layer, then you will not use ReLU. Then you will use either the linear output unit or softmax or sigmoid, depending on what you're predicting. But in all the hidden layers, you will use a ReLU activation function. Now, to be fair, the sort of application that I have to cover in this lecture from the recent macro literature actually doesn't use the ReLU function. It uses what is known as a soft plus function, which is sort of like a closed differentiable cousin of the ReLU function. So this is a diagram. So ReLU is the same as plotted before in blue, and this green function, which is has the sort of equation log of 1 plus epsilon exponential of z. You exponentiate z, add 1 to it, and then take the log of it. You get this kind of green kind of function, which looks like a very close differentiable cousin of ReLU, and sort of differentiable everywhere and sort of smooth and so on. But in the machine learning literature, I was reading that the soft plus function actually is not recommended. And that's what the Goodfellow textbook says, that even though they discuss the soft plus function, but they say you should not use it because it doesn't tend to work well in practice. Yeah, so there were some questions. I should answer them at this point. So like 2 or 3 people have said this. Yes, definitely. So I am recording this, and we will have this available, the recording available. Just like the first 2 lectures, we will have the recordings available on YouTube, and the lecture slides are already available on my GitHub page, which is already in the chat. So yeah, so you don't need to worry about that. Okay. Um, so um, so as I was saying that the sort of soft plus function, even though it looks like it looks like a very close cousin of the ReLU function, it appears as if one could do nothing much wrong if you use the green function as opposed to the blue function here, because you have the added benefit that it's differentiable. But actually, no, the soft plus function is not recommended by the machine learning guys. However, Jesus Fernandez, who is one of the best computational economists, did use the soft plus function in his 2020 paper, in which he solved a heterogeneous Asian model using neural networks. And this is why I have it over here. Otherwise, I wouldn't even be mentioning it because it's not used commonly. It's in fact discouraged in the ML literature, but for reasons that have to do with the difficulty in sort of solving the Hamilton-Jacobi-Bellman equation and the kind of applications that we have in economics where differentiability is important. The kink, in the value function is hard to deal with, and because it becomes non-differentiable. So even if you have non-differentiability at one point, it creates complications. So Jesus Fernandez, who is a professor at Penn, he in his paper did use a soft plus function, and he did not use a ReLU function, even though he recognizes very clearly in the paper that that is naturally the default choice in the ML literature. But since this is for economists, I thought I should have this function as well, because top people in the field of economics are using it, even though it's discouraged in machine learning in general. Okay. Now, the next thing is that we've talked about output units, we talked about hidden units, and the fact that ReLU is the natural default choice. So if in doubt, use ReLU, okay? If you want to follow Jesus, and if you have a kind of application in which the kink in the ReLU function is creating a lot of problems, then you may use the soft plus function, and so on. Okay. But actually, I'm not sure, because in the Jesus paper, people have just started using neural networks for estimating nonlinear DST models. So this is really at the frontier. And this paper that I'm talking about is still a working paper. Actually, it's not even yet being published. And so, and therefore they start a relatively simple sort of policy function that they're trying to learn. They're just trying to learn a function of two variables, and they actually just use a neural network with one hidden layer. And so it could be that if you're trying to solve a high dimensional problem with many layers, just like in the machine literature, the soft plus function will actually not work. But definitely that paper, they use the soft plus function because they were just learning a relatively simple, not simple, but relatively low dimensional. It was highly nonlinear, the function, but it was low dimensional. So they just needed a one layer. The one hidden layer was enough. They didn't use a particularly deep neural network in the paper that I'll discuss later today. Okay. Now, we already discussed that we have this okay, let me go back to this diagram. We already discussed that the depth of the layer has to do with number of functions that are composing, right? So the depth of the layer is 2 in this case because you have 2 hidden layers, right? On the other hand, the width of the network has to do with the number of hidden units per layer, right? So in this case, you have 4 number of hidden units in each of the layers. And this is completely symmetric. So you have the same number of hidden units, and that is a standard case across all the layers. Okay, that is the width of the network, which is 4 in this case, and the depth is 2 because you have 2 hidden layers. Okay. And another thing that we need to discuss, these are 2 things. The third thing that should be obvious that we need to figure out in terms of network architecture or the structure of the design network is the sort of patterns of interconnections between these layers, right? One, number of layers to use. That is one choice we need to make. 2, the width, which means the number of hidden units within each layer. And these hidden units, like these blue balls and green balls, are basically, these are the neurons essentially. These are comparable neurons in the brain because they take inputs from 3 different inputs in this case, and 4 different inputs on the last hidden layer in this case, and they output an activation value. So it's a vector. Each one of these hidden units can be thought of as a vector to a scalar function, Rn to R1, let's say, and that's like comparable to what neurons do in the brain. So we need to decide what is the width, which is the number of hidden units in each layer, the depth, number of hidden layers. The third thing is the pattern of interconnections between these networks, right? Between these hidden layers. So, right. So, you might ask, how should we choose this? So So it turns out that the deeper networks can use far fewer units per layer because they have more number of layers, right? They're, let's say, 5 or 6 or 7 as compared to a 2 or 3 or one hidden layer neural network. So if you're talking about a deeper network in general, uh, they need far fewer hidden units per layer in order to learn a function of the same kind of complexity. Okay, and also they have some nice properties in terms of generalization. When you have deeper networks, they tend to be efficient in the sense that they generalize very well, and they are able to approximate far complicated nonlinear functions. And that has been the sort of success of the recent deep learning literature, that we've started using these so-called deep networks, and that is why actually we've become sort of successful. The whole point is that we need deep networks. If we just have one layer, or like, then you can only approximate relatively simple functions. Actually, I'll come to an interesting point, but so really there is no sort of general theory which is going to tell you the optimal number of network hidden layers that you should use, or the optimal depth. It really varies by application. So for example, in the Jesus paper that I'll discuss today, they just use one hidden layer because they're trying to approximate a function which is only a function of two state variables, and so on. Width, on the other hand, depends on the depth. So if you have a network which is very deep, so the width needs to be low in that case. You don't need a very large number of units. Otherwise, that will just be a computationally inefficient choice, right? And computational constraints are very relevant when we're doing neural networks because we only use them for highly high dimensional, highly computationally intensive, highly nonlinear tasks. So, for example, the Jesus paper that I'll discuss later today that I keep coming back to, it takes 3 weeks to actually. So, if you run the code, just relax for 3 weeks, and then it takes 3 weeks to run the code and to estimate the function. So, I was actually saying that they do a simple thing. They just use one hidden layer, but it's still sort of, and they just have a function which is a function of two state variables, but it still takes them 3 weeks. Okay. Um, so then we have this beautiful universal approximation theorem. And I just said that, in practice, one tends to use deeper networks because they help you approximate more complicated functions better and so on. And you need a smaller number of hidden units per layer. And also the composition of functions that you're doing, each one of those functions can be relatively simpler, right? Because you can think of neural networks really as trying to decompose the complicated problems into various smaller steps, right? So essentially, if you have a deep network, then you can have, you can learn the same level of complexity with a large number of layers, but each one of those layers can do something very simple, right? Division of labor, essentially, across the layers can be very efficient in that case. So it's true. However, you have this beautiful theorem, so-called universal approximation theorem. One of the few really powerful results that we have, theoretical results in machine learning by Hornick and other people as well. So it says that if you have a feed forward network, which is what we're talking about, not a recurrent network, and if it has a linear output layer, so that you're solving a regression problem, you're not using sigmoidal or softmax kind of output layers. If you have a linear output layer and a feed forward neural network, and even if you have one hidden layer, at least one, of course, more than one is possible. But even with one layer, even if at least one, so that it also works for one. Even if you have just one layer, and of course it works for more layers, but even works for one layer. If you have one hidden layer with any squashing kind of activation function, such as logistic or at hyperbolic tangent and so on, you can approximate any Bohr measurable function from any finite dimensional space and so on, with a non-zero amount of error. Of course, you won't get exactly zero error, but like you can by increasing the number of hidden units in this one hidden layer, you can get better and better approximations, and actually you can get arbitrarily precise approximations. This theorem sort of reminds me of the Weierstrass theorem in calculus. And those of you who are done real analysis would know that the Weierstrass theorem guarantees that you can approximate any function with a polynomial with arbitrary degree of precision. And this is sort of very similar to that. And actually, you could essentially think of them as generalization of polynomials. Of course, these are not polynomials. These could be very highly nonlinear complicated functions. But essentially, it's very similar. You can approximate any function. But in this case, your function approximator is not polynomials, just as in the case of Taylor's theorem from calculus, Weierstrass's theorem, but it's sort of a neural network which has these layers. So in theory, even if you have one hidden layer, you could approximate any function out there that exists in the world as long as it's bored and measurable, which almost all functions that we're dealing with are. We're not doing anything funky. And you can do this. You just need one hidden layer. In theory, even one hidden layer is enough. And the universal approximation theorem guarantees that, you will be able to approximate this function to an arbitrary degree of precision, even if you just have one hidden layer, which is sort of beautiful. But in practice, this is just a theoretical guarantee, right? This does not tell you whether you're likely to converge in the right amount of time in practice to that solution, or it doesn't give you any guidance regarding the number of hidden units you need. And in practice, which makes a lot of intuitive sense, if you just have one hidden layer, then you might need a very large number of hidden units in that one layer if you want to make good progress. And that becomes often computationally prohibitive. So in practice, we don't tend to use, unless you have an application which this works fine. For most complicated applications, we have deep neural networks in which have a lot of different layers. And this helps us minimize the number of hidden units per layer. And the universal approximation theorem, of course, continues to operate. But of course, as I said, this is a theoretical result, right? So for example, in calculus, we know that any function which is continuously differentiable and so on, it can be approximated with any polynomial. But the Taylor's theorem doesn't actually tell us that, how to find that polynomial. The same way, the universal approximation theorem doesn't tell us how to find that function. It is just what is known as an existence theorem. So we don't know in practice what kind of optimization algorithm to choose to find that f star, which is very close to f, arbitrarily close to f, even if we know that it exists in theory. But the fact that we know that it exists in theory is very comforting, because if you don't even know it exists, then what's the point of looking for it? But the theoretical guarantee is sort of comforting, because at least you're trying not to search for something that exists out there. Okay. As I already said, in practice, if you have a larger, deeper model with higher depth, that reduces the number of units that you need per hidden units that you need per layer, and so on. And often such deeper networks tend to perform really well in approximating nonlinear functions, and also tend to have lower generalization error. However, but deeper networks are harder to optimize, right? Because you need to use back propagation, and that complicates things if you have a deeper network. So you have this trade-off, but they have some benefits as well, which we discussed. Okay. The last point is the network architecture discussion is how to connect two layers, right? So, so that really depends on the matrix, on the weight matrix W, okay? So if W is a sparse matrix and has lots of zeros, then you're not connecting every neuron or hidden unit, which we can also call a neuron, or hidden unit is just a neuron. You don't need to connect every neuron to every other neuron out there if W is very sparse. But in practice, in most applications, we don't have very good a priori information in terms of what should be the specific pattern of sparsity that one should use. So therefore, in practice, we don't really have lots of zeros in a priori sense. We just tend to approximate these parameters. All of these are parameters. But if we just a priori set a lot of these values in W equals to 0, then we have fewer parameters to learn, and that will be very helpful. So for example, actually in sort of, visual recognition tasks, this is very interesting. In convolutional networks, which we won't cover, but you can read about them. And MIT has these open courseware lectures on convolutional networks online. And so these are modeled on the, pattern of what we see in the animal visual cortex and also the human visual cortex. And you have these particular patterns of sparsity across these hidden layers. And in that context, we have some information about the problem at hand, which is, a visual recognition problem, in which case we know the specific pattern of sparsity that we need to use because of things like tilting and light patterns. with the visual cortex and things that I can't go into. And in that context, we are able to impose a lot of zeros in these weight matrices, and that helps us because we have to estimate fewer parameters. But in general, we generally just don't have any idea about this in terms of how, because it's a black box, how we should connect two layers. And we just have a matrix W which determines this. And if the algorithm, because of the optimization routine, just naturally estimates a lot of zeros in there, then I mean maybe the sort of the black box is choosing a sparse structure, and maybe that works, but we don't have an idea about this in general. Okay, I think I need to speed up. Um, so I need to really discuss backpropagation and stochastic gradient descent. That's the main thing that's left. And then we are going to go towards like regularization, for which I don't have time. There's nothing new in regularization, so let's discuss this first. There's nothing new in this. We already discussed lasso and ridge regression in lecture one. So just like in other machine learning algorithms, because of the cross validation, because you need to do cross validation and you need to solve the variance bias trade-off and the overfitting problem, you will add some sort of penalty term in the loss function, which will and that is what you will optimize. That is the loss function that you will minimize. However, if you remember lecture one, we had this lambda parameter which you had to tune using cross validation, but it's very computationally difficult to do this with deep neural networks. And cross validation is not very easy to do in the context of deep neural networks. So actually a more common method is to use what is known as early stopping algorithm, where you split the data again into training and validation samples, just like cross validation, but you run your gradient based optimization on the training sample, and you stop when the prediction error in the validation sample at the particular iteration starts increasing, and you early stopping, and then you stop, and that's where you find the optimum parameters. And this is a way of regularization basically, because if you don't use this, then you may learn too much and you may sort of overfit. But that's really all I have to say about regularization. You could read chapter 7 from the Goodfellow textbook, that is the main reference for more details on this. They have the whole chapter on regularization, but we won't have a lot of time for this. But the main thing that I really want to discuss, is sort of because that's more important, is backpropagation and stochastic gradient descent. So the thing is that we have to use gradient descent in order to learn the parameters theta of which the loss function depends on, which will lead to a minimization of the loss, right? Um, and in order to implement a gradient descent kind of algorithm, we need to compute the gradient, of course. But evaluating a gradient is very computationally expensive, especially for deep neural networks, right? So we have this sort of beautiful recursive solution, which is known as a backpropagation. And even though this is used a lot in neural networks, but this is not necessarily restricted to neural networks. And backpropagation should not be thought of as something very special to neural networks, but it's used a lot in neural networks nowadays. But because it's complicated and computationally intensive to compute gradients in this context. But otherwise, in general, backpropagation is just a general way to implement gradient computations in a computationally efficient or less costly manner, right? Um, so as we said, we're talking about deep feed-forward networks throughout this lecture. We're not talking about recurrent networks, which are used in computational linguistics, in which information can even flow backwards as well as forwards, and there can be these two-way connections in an acyclic graph on these um, computational graphs. So we're not covering that. So in the deep feed-forward networks, information is flowing only forward, right, from the input, and then you apply the transformation F1, then F2, all the way to Fn. It's only flowing forward, right? Feed forward. And ultimately, you get a loss and so on. Ultimately, you get the output, and then from the output, obviously, use the depending on your output units and depending on the loss function choice. Let's say the negative of the log likelihood, you get the loss function. But what backpropagation does is that even though in the actual neural network, information is only flowing forward, it's not flowing backward. But backpropagation as a computational strategy only, not in terms of what's happening in the neural network, but simply as a strategy to compute, as a recursive strategy to compute the gradients, it allows information to flow backwards through the network as well. And so backpropagation, as said, should not be thought of as a whole learning algorithm. So we have the gradient descent algorithm, And the back propagation is a intermediate step. It is a particular step that we are taking in the whole learning algorithm, which is helping us just compute these derivatives using chain rule in a computationally efficient way. And the back propagation is not a learning algorithm in and of itself, but it is just a method for computing derivatives efficiently. But it's really efficient method. Okay. So what happens is that you have these computation of functions, right? So if you have y, let's say y is the output unit. Well, actually, z is the output unit. Z is the output unit in this example. And if you have y, which is actually the intermediate hidden layer, let's say, and x is the input. So you apply the function g, and then you apply the function f on y and so on, where y is n dimensional and x is m dimensional and so on. We know from basic calculus that chain rule means that if you want to evaluate a particular derivative, I'll just skip this. And this is just the second one is just the gradient notation version of the first one. Um, so if you just want to evaluate the gradient of derivatives of z with respect to its arguments x, where this is just a vector of partial derivatives, the gradient vector, from basic calculus, we know that chain rule implies that first we need to differentiate y with respect to z with respect to y, and then y with respect to x. Okay. And if you just this is because this is in gradient vector notation and gradient vector form. The partial derivative is dy over dx, which is just a Jacobian of the y function with respect to x. Its argument will just be a matrix of m by n dimension, and it will, yeah. And you transpose that, and then you multiply it with the n by n vector, n by 1 vector, or whatever the dimensions are, of partial derivatives of z with respect to y. And that's how this is basically just chain rule, right? Where in our context, z is basically, you could think of as the loss function, let's say, right? Yeah. So you can think of y as essentially as the output unit, and then f is some function being applied on that, where z is the output unit, loss, yeah, not output unit. Y is the output unit, because usually we want to compute the gradients with respect to the loss function with respect to the parameters, right? And yeah, or with respect to any hidden layer. So when we do this, we have to apply chain rule, because we have this composition of functions in the machine, in the deep neural network structure. And the problem is that if you just don't use any back propagation, if you just simply try to compute this, you have these redundancy of sub expressions, which can actually grow exponentially. And this will become clear when we look at the graph. So UN here is let's say the output unit or the loss function. Let's say our objective is to compute the partial derivative of UN with respect to, let's say, U1, U2, U3, and various parameters, nodes in this computational graph. So let's say you want to compute the derivative of UN with respect to U1, right? When you do this, because of this, and these arrows are indicating connections, right? So for example, the two arrows going with U1, if they go to some U2, it means that, um, this is how the this is basically representing the connections and the compositions between all of these hidden layers. It's a computational graph representation of a neural network. So first you need to differentiate, if you want to know what DUN over DU1 is, okay? First you need to differentiate DU1 with respect to DUJ, and then DUN with respect to DUJ, and you multiply that. Just chain rule, right? Now the problem is that if you do this once and don't store any expression, and then second, and the next derivative that you're interested in is DUN over DU2, right? But DU2 could also be ultimately, because of the sequence of compositions, be connected to this, this layer or the same UJ. And then you'd have to compute DUN over DUJ again, right? And that is sort of computationally redundant because you already computed it. So what, right? So you have these sort of redundant expressions, and in a deep network, actually, these number of wasteful computations that you have to repeat impose a computational burden which can even grow exponentially. The beauty of back propagation is that rather than recomputing them, it sort of uses a recursive structure, and it stores all of these intermediate derivatives, dun over duj, and so that it basically goes from each edge of the graph and visits each other edge from ui to uj exactly once. So for example, it's not going to compute the DUI over DJ link more than once. It's going to exactly compute once. So the number of computations will go only linearly in the number of nodes, grow only linearly in the number of nodes. And that doesn't happen. It may actually grow exponentially if you don't apply backpropagation, right? Um, so mathematically, as I said, you want to compute DUN over DUI, which you could think of essentially as, let's say, UN could be the loss that you want to look at the how the loss changes if you change the parameter by a bit. And what you do, and you're interested in computing the gradient dun over dui, where I goes from 1 to m, 1, 2, 3, 4, capital M, where these are the first m sort of nodes, right? Starting from u1 all the way to u2, u3, and so on. Um, the first m nodes. So you want to look at the partial derivatives, all these m partial derivatives of the loss function, let's say, with respect to these m parameters, the first m nodes. And we, without loss of generality, we just arrange the nodes in such a way that the m nodes with respect to which you're interested in, these m partial derivatives, are ordered first. They are u1, u2, all the way to um. And the m plus 1 all the way to capital N number of nodes, which are not in these m, not in this set of m derivatives. You're not interested in those partial derivatives directly, but you will need to compute them because of chain rule. And okay, another piece of notation that I need to introduce is a function f. F is just a function which is, we have all these compositions, right? So I should write fi here because there are various functions. But if all of them are equal to each other, then you can just work with f. So AI is just a set of parent nodes of UI. So in the graph, for example, if you have UI, which is this one, right? This one, the one that I have to which all of these four arrows are pointing. If UI is this thing, then this set, which is sort of highlighted and encircled and has these four sort of nodes, is the parent set of UI, because these are the four nodes which map from directly into UI, right? So if you apply the function fi on these four nodes on the on the if it's r4 from r4 to r1 function, if you give it these four inputs, it's going to map the parent nodes is going to map it into UI. So the parent nodes are just a set of nodes such that fi of AI is equal to UI, where AI are the parent nodes of UI, or all the nodes uj which belong in the set AI are parent nodes of UI, where j are the parents, I is the child node. Okay, so the chain rule implies, as I already discussed, graphically, that you need to go from here to here and then here to here and eventually to un. You need to have all of these, you need to multiply all of these terms because of the chain rule. So if you want to understand what dun over duj is, where j, remember, only are the parent nodes, as I said. So in this context, j is from 1 to m. You just need to multiply these terms and add them up if you want to apply chain rule, because you need to understand, if you want dun over duj, you need to compute dun over dui, multiply that by dui over duj, because that's what chain rule says. The only thing is that um, you add these terms across all I, only those I, such that J is the parent node of UI. Why? Because you're ultimately interested in the partial derivative of UN with respect to UJ, right? So you're only interested in children node of UJ, right? Because UJK children role, whatever are the childrens of UJ, will only be the nodes with which UJ is directly interacting. Others are irrelevant. So you're interested in all the I, where I are the children and J are the parents, and you're differentiating with respect to the first M node. So these are the parent nodes. So you're interested in the derivative of the loss function with respect to these parent nodes. And in order to apply chain rule, you need to know who the children are. So you only look at all the nodes I, such that J is the parent of those nodes I, right? So for example, if you're interested in that partial of U with respect to this node, you only look at these two nodes, for example, because only these two nodes are the parent or the children of uj, and you only need to compute dui over duj for these two nodes, and then multiply them by dun over dui. So what a back propagation does is that it computes the sort of the m derivatives dun over dui for the children um, in a forward computation step and stores them. And in the actual implementation, once you've done the forward computation, you just need to compute dui over duj. You don't need to compute the first term because these are already computed and stored because this has a recursive structure. You go backwards, basically. You start with the output layer, go backwards, and ultimately, and uh, yeah, you go backwards, and dun over dui have already been stored, and then you only need to compute dui over duj and multiply it with the already existing and stored dun over dui and then add them up. So in each iteration, you just need to multiply a term, compute a partial derivative, and add them up. And you don't need to compute these partial derivatives again and again. And that is a form of computational efficiency. So this is the algorithm. You can have a look at it. Uh, but the main thing is you have two steps. You have a forward computation step, which is starting from the first m nodes with respect to which you're ultimately interested in taking the partial derivatives, and just applies the functions based on the parents and on these first m nodes and figures out all the m plus 1 all the way to capital N nodes, the last n minus m plus 1 nodes. And by simply applying these functions, and it also computes derivative of all these derivatives un with respect to ui for the first m, for m plus 1 all the way to n. And then there's a backward computation step in which you start from dun over dun, which is just 1, and then dun over dun minus 1 and all the way to du1. And in this, you have this efficiency because when you're trying to compute dun over duj in the backward step, this is what you need to compute. But from the forward computation step, you've already stored all of these partial derivatives, and you just need to visit this edge between ui and uj exactly once, and you'll get all of these partial derivatives that you need. And so that's how we sort of exploit the recursive structure in which you'll have to um, you will have to minimize on the computational sort of complexity. Okay, so as I said, the back propagation is just the way that you compute this gradient. This is grad theta. That's how you compute it using back propagation. But that's not the whole algorithm. In actuality, using some sort of gradient descent algorithm in which you're updating the parameters theta given the loss function that you have, right? And given, of course, the loss function will just depend on the output, right? By and the output depends on this whole composition of functions that is a neural network. And yeah, so you take the gradient of the loss function with respect to the parameters, then you updated the previous theta in the direction of the gradient, and this is known as a gradient descent algorithm. And epsilon is just a parameter which is a learning rate. So for example, which is dictating a learning step. So if you have a simple function, if you try to learn it, you want to minimize the cost, you want to find the w parameter which minimizes the cost, and you start with some initial random value for theta. You keep updating the direction of the steepest gradient, steepest direction, which is the gradient direction. And choice of epsilon is important. And I don't have a lot of time for this, but we want to optimize this properly. There is no theoretical sort of guarantee for what sort of epsilon you should choose. This is really sort of trial and error. But you don't want epsilon to be too low because then learning is too slow. It may take a lot of time. If epsilon is too high, then you just get a lot of fluctuations and oscillation, and you might not converge to the minima. You might keep hovering around it and cycling around it and not converge to the local minima, for example. Okay. A last important idea is stochastic gradient descent. Um, the thing is, the standard gradient descent is just standard, right? That is something we know from previous sort of calculus as well, and sort of we know about gradient descent algorithms. But in the context of neural networks, especially when you have deep networks, there can be lots of different observations, and also when you have large training data, right? So if you're just doing this sort of plain vanilla, what is known as a batch gradient descent, and you use the entire training data, right? Then you need to compute all of these, let's say t is of a dimension, I don't know, n. We have n number of data points in the training data from t goes from 1 to n. You need to compute all of these n because this is a sum of of gradients, and then you need to update. So it takes a lot of time to just make one. Even in one iteration, you need to use the entire sort of training data, and that is very computationally burdensome for deep neural networks. So what we tend to use is that the most commonly used algorithm for learning deep neural networks is stochastic. That is the default. In fact, even if you use a function in R, the default would be to use stochastic gradient descent, SGD as it is called, along with backpropagation. So what we do here is that rather than using the entire training data for gradient updating, we just use a random subsample of the data, which is also known as mini batch gradient descent. And there are some theoretical reasons why I don't have time for those. But basically, if you have dealing with IID data, then because of things like central limit theorem and other reasons, the standard errors, the gradient descent is only growing in the order 1 over under root b. So that increasingly, and it makes a lot of intuitive sense, because if you have IID data, then all the distributions are the same. So each additional observation is not giving you a lot of marginal, not giving you a very high marginal new information about the distribution, because this is IID data. So further observations become increasingly redundant over time. And therefore, the fact that using a random subsample, not the entire data, is not actually very costly, because computation time is going to grow if you have B observations. If you're computing B gradients in every step, then computation time is going to grow the order of B, and that's very costly. But because of things like central limit theorem, things like law of large numbers for IID context. I mean, even if it's a martingale, you can have law of large numbers for martingales. You sort of increasingly redundant information. So therefore, this is basically there's a computational efficiency argument, and yeah. So if you have very large data, as I said, it will take a lot of time to just calculate one gradient and do one updating step. But stochastic gradient descent at the same time might have made many steps, and if you've designed it correctly and if it works in that context, then it may come closer to the truth. And you can see this reference for a more formal analysis of why stochastic gradient descent works. Okay, so the algorithm is that um, while, of course, some stopping criteria is not met, which would be some sort of distance between the loss function and some sort of performance criteria on the loss function, the validation set, and eta is the learning rate. This is an important parameter. Theta is a set of parameters that you want to learn. So by the way, in our sort of deep neural network, theta are all of these weights and biases, right? W, B, small w, C, in the simple case. All of the parameters that show up in all of these composition of functions, and these are called weights and biases. W is weight and B is for bias. These are constants which are added, intercepts, as well as the parameters. All of these compose theta, and theta is composed of all of these weights and biases, which are parameters that you need to learn in order to train the neural network. Training the neural network means learning these parameters. That's what you're trying to learn. What we're trying to learn in a neural network is these parameters. So rather than using the entire data, you use what is known as a mini batch of M examples. Again, what is the value of M? Typically 64, 128, these kind of values are used, but that depends on the application. You sample a mini batch of M examples from the training set at each step. So there is some randomness in this, right? Because in the next step, you could sample a different M set of examples. And that's why this is known as stochastic, because there is a randomness in the updating step. And this might actually have some benefits as well as some costs. Okay. So initially, let's say your gradient is 0, and for example, and then for the loop will obviously only go from 1 to M, because you have M examples. And at this one iteration, you will, in order to perform one updating step, you will compute these M derivatives, and then you add them up. So by the way, this is actually, you might say, well, where is the sum? Well, there's no sum because the loop takes care of that. You're recursively adding these things. So essentially, you are summing up all the gradients with respect to the M observations, but there's no sum here because there's a loop which takes care of the fact that you keep on adding the new gradient in a G, and ultimately you get the value of G. And then you update theta in the direction of G, which is what the gradient direction is, updated gradient step is. And then eta is a learning parameter. And there's a minus here, by the way, because you're minimizing loss function. So you want to, if you're maximizing, this would be a plus. Eta is very important, but we need to experiment with this. Learning rate is very important. If the learning rate is too high, you can get oscillation and lack of conversions, or may take a lot of time. You just may be stuck in some sort of cycling around, sort of moving up and down around the local minimum without ever actually converging to it. But if eta is too low, then it may take a lot of time. Okay. The last thing is the stochastic gradient descent with momentum. I don't have a lot of time for this, but because there was a lot of randomness in the stochastic gradient descent, right? Because we are choosing these m samples at each stage, and this can create problems because, especially for certain kind of curvatures in the space input space that I don't have time to discuss, when you have these ravines in which the gradient is very steep in one direction but not in other directions, then the randomness could mean that you're never going to in a persistent sense with momentum approach one direction. So sometimes we use what is known as stochastic gradient descent with momentum, because we get faster conversions and reduce oscillations, and we move towards one direction with momentum. The same algorithm, the only difference is that the first half is the same. You also have a new parameter v, that's the main difference. So you have a velocity parameter, and you, rather than theta being equal to theta minus eta g, which is what we had previously, you have theta alpha times v minus eta g. So minus eta g is the updating step, and alpha times v is a persistent. Just like in the AR1 process in econometrics, we have that xt plus 1 is rho times xt. Essentially, this is v is the same thing as alpha times v. For alpha is usually chosen to be something like 0.9, and so there's some momentum. So there is some momentum, and so you're linked with the past, and that reduces the randomness and so on. So we won't have time for discussing economic application number 2, but I have it in the slides and you could read the paper. But we'll discuss this. Okay, so I mean, sort of the details of the paper are not important. So this lecture is not about non-linear DAC models. It's not about macro finance. You can read the paper; it's a cool paper. But if you want, and I sort of won't discuss the sort of motivation behind the paper and so on. I have some of that in the slides, but you can read the paper. But basically, my point in this context, the context of this lecture, is to illustrate an application of deep neural networks and recent economic literature, right? So in this paper, what they have is they have a nonlinear DSG model in continuous time. So they have a Hamilton-Jacobi Bellman equation as opposed to a Bellman equation. They have heterogeneous households which have idiosyncratic shocks which are uninsurable and so on. They have a representative firm and a representative finance sector and so on. And they have some financial frictions in the model, and I don't have time for this. But basically, they want to understand the impact of leverage on the macroeconomy. And they have multiple stochastic steady states. It's a nonlinear model. There's endogenous regime switching across the two states in the model. There's time variation and the volatility and skewness, super cycles of borrowing and deleveraging. So I won't discuss these things in detail, but the point is, you could read the paper, that it's a very complicated nonlinear DSG model with multiple stochastic steady states, and there is endogenous regime switching going on across the two steady states, stochastic steady states, not deterministic, in which they have one is a high leverage steady state in which the economy might be stuck when there's high leverage, and recessions in that kind of steady state will be very severe, and then you may have a low leverage steady state. But the details of the model are not important. What's important is that they use this, we have these global solution methods, for those of you who are familiar with macro. And typically we tend to use sort of perturbation methods, so Taylor approximations essentially. And we have other methods like value function iteration and projection methods, so on, in which we use Chebyshev polynomials and things of that kind. But what they do is that they train a deep neural network on the samples. In this case, the training data is very interesting, right? Because this is a theoretical model, so they actually don't have any empirical data, right? So this is a very cool application, because the data on which the deep neural network is being trained is the samples from the ergodic distribution of the model. So it's not empirical data, it's theoretical data. And they train the deep neural network on this data, and they And since the perceived law of motion they're trying to approximate, which is the function of state variables, is very nonlinear in the state variables, it's very complicated, and they don't know what sort of function to use. And they also show that typically Chebyshev polynomials, which is what we use to learn these kind of projection methods, actually fail in their context because their model is very complicated. And even Chebyshev polynomials, they show in the paper, they fail and they only perform well on the subset of the sample space to which they visited quite often in the samples of the ergodic distribution. But the Chebyshev polynomials don't generalize very well across other domains. But as we know, deep neural networks is a machine learning technique, and they are very good at not just fitting the data, but generalizing as well. And so they are able to generalize in the entire state space, even in those as subsets of the state space, which you didn't have a lot of, which you did not visit very often in the draw of samples to the ergodic distribution. So they're able to do this very well using deep neural networks. So again, I there's no point in reproducing the derivation from the paper. Read the paper for the derivation. But the main point that I want to make is that they have this law of motion for debt in their model. BT is debt. WT are real wages, real interest rate, consumption, and PT is debt. DPT is the change in debt. It's a continuous time model. This is the actual law of motion of debt in the model. And since they're using a sort of learning type model, there's a perceived law of motion of the households. I don't have time for this, but a Russell-Smith algorithm is a very common algorithm which is used to solve heterogeneous Asian models in macro, and that posits that households are using only a finite set of moments in order to learn the infinite dimensional cross-sectional distribution in this heterogeneous Asian model, and in order to form their expectations. So they only work with n equals 1. So the households are just looking at the first moment, which is just the expectation of the law of motion DBT, conditional state variables, debt, and labor, aggregate labor, R's. And what they are trying to basically approximate is H of BT through the neural network. H is the function F, actually, from our previous notation that we want to understand. This is the perceived law of motion of the household, and you want to understand this. And so basically, H of BT is a function that is the perceived law of motion of the expectations of the households regarding the debt, law of motion of the debt. And that is what they want to understand. So they simulate the data from the ergodic distribution of the data of the model, and then they use a neural network with one hidden layer. So as you can see, this is actually phi. As I told you in the beginning of the lecture, they actually use a soft plus activation function. So this layer is S, by the way, is inputs. So S is the state variables. I just finished in 2 minutes. Um, okay. So I'll just wrap it up after this slide. So a neural network, they use a neural network with a single hidden layer. Inputs are state variables. They use the activation function of soft plus, one hidden layer, and they use stochastic gradient descent. Oh, they don't use stochastic gradient descent. And so, but for reasons that I don't have time for, but they don't want to introduce randomness in their estimation. But ultimately, they're able to approximate H and solve the model using this nonlinear DST model method. And that's all that I have to say. And I mean, as I said, it's not very hard to implement relatively simple neural networks in R. There are some website links given which help you visualize neural networks and tweak and play with them online an active learning sense. And then there are other packages that I mentioned here. And I have given some pseudo code in which you just specify the number of hidden layers and activation functions, which are ReLU is for rectified linear unit and so on. I don't have time for this, but basically it's very easy to use the MXNet package, for example, from R. You can find functions which will train neural networks for you, given a specification of the number of layers, the width, the choice of activation functions, choice of output unit, and you can predict and you can train the network on the training data and predict on the test data and so on. So I'll end the lecture here, and I have a lot more material, slightly more material than we were able to cover, and you can read that on your own if you want, and I am happy to answer questions at this point. Yeah, of course, we'll share the recording. Yeah.
So if there is any questions, please use the raise hand option. Okay, I believe there are no questions. So let's wrap it up here. Sonan, maybe?
Yeah, if there are no questions, then we can wrap it up. And
Okay.
if you have any questions, then you can send an email, of course. If you figure out a question later, then you can always send me an email. Okay. Nonlinear DSC model, how we can apply particle filters, and what do particle filters do? So particle filters, I mean, not really related to ML. So this sort of, so we have this Kalman filtering, right, which is used, and this is particle filters, sort of a non-linear filtering as opposed to Kalman filters, which is a kind of linear filtering. Yes, so particle filters are used to solve DSC models, and actually, yeah, so for computation and solution DSC models, and that's a technique that is used in computational macroeconomics, and they are very complicated nonlinear filters which help you figure out the law of motion of the hidden sort of latent variables and factors of variation. But just like you have Kalman filters, um, so this is not really relevant from a machine learning kind of perspective. But yes, you use particle filters to solve and compute nonlinear DSC models. That's true, and maybe Dr. Adnan knows more about them than I do. But yeah, but it's not an ML topic. Yeah. Okay. Any more questions?
Thank you, Sonan.
Okay. Yeah. Okay, so I'll just end the lecture and we'll make the recording available. Okay.
Okay, thank you very
Okay,
much, everyone,
thank you.
for joining. Yes, sir.